For this first discussion of scheduling algorithms, I want to focus on what we call run-to-completion scheduling. This type of scheduling assumes that as soon as a task is assigned to a CPU, it will run until it finishes or until it completes. Let me list first some of the initial assumptions we will make. We will consider that we have a group of tasks that we need to schedule. I'll refer to these also as threads and jobs and similar terms. Let me also, to start with, assume that we will know exactly how much time these threads need to execute. So there will be no preemption in the system. Once a task starts running, it will run to completion. It will not be interrupted or preempted to start executing some other task. And also, to start with, let me assume that we only have a single CPU. We will relax these requirements further as we go through this lesson. Now, since we will be talking about different scheduling algorithms, it will be important for us to be able to compare them, so we'll want to think about some useful metrics. When it comes to comparing schedulers, some of the metrics that can give meaningful answers regarding those comparisons include throughput, the average time it took for tasks to complete, the average time the tasks spent waiting before they were scheduled, overall CPU utilization. We will use some of these metrics to compare some of the algorithms that we will talk about. The first and the simplest algorithm we'll talk about is first come, first serve. In this algorithm, tasks are scheduled on the CPU in the same order in which they arrive, regarding of their execution time, of load in the system, or anything else. When a task completes, the schedule will pick the next task that arrived in that order. Clearly, a useful way to organize these tasks would be in a queue structure so that tasks can be picked up from it in a FIFO manner. Whenever a new task becomes ready, it will be placed at the end of the queue, and then whenever the scheduler needs to pick the next task to execute, it will pick from the front of the queue. To make its decision, all the scheduler will need to know will be the head of the queue structure and how to dequeue tasks from this queue. So basically, for first come, first serve scheduling, some FIFO-like queue would be a great run queue data structure. Now, let's take a look at a scenario in which these three tasks, T1, T2, and T3, have the following execution times. T1 is 1 second, T2 is 10 seconds, and T3 is also 1 second. And let's assume they arrive in this order. So T1 followed by T2 followed by T3. So this is how they'll be placed in the run queue. Now, let's look at throughput as a metric for this kind of system that uses the first come, first serve scheduler. We have three tasks. To execute them one after another, we will take a total of 12 seconds, 1 plus 10 plus 1. So the scheduler on average achieves a quarter of a task per second, so 0.25 tasks per second. If we're interested in the average completion time of these tasks, the first task will complete in 1 second, since it will start immediately. The second task, it will complete at time t11. It will have to wait 1 second for the first task to complete, and then it will execute for 10 seconds. And then the third task, it will complete at time t12 because it will have to wait for the 11 tasks for T1 and T2 to execute until it starts and executes for 1 second. So if we compute the average completion time in this system, we see that it is 8 seconds. If we're interested in the average wait time for the three tasks in the system, then the first task started immediately. The second task started a second later because it had to wait for T1 to complete. And then the third task had to wait for 11 seconds before it started executing. So the average wait time for these three tasks is 4 seconds. So we have a simple scheduling algorithm. However, probably we can do a little bit better in terms of the various metrics that we are able to achieve with this algorithm when we try something else. So we see that first come, first serve is simple, but the wait time for the tasks is poor, even if there is just one long task in the system that has arrived ahead of some shorter tasks. So to deal with this, we can look at another algorithm that's called shortest job first. And the goal of this algorithm is to schedule the tasks in the order of their execution time. Given the previous example with tasks T1, T2, and T3, the order in which we want to execute them would be T1 followed by T3 and then T2, the longest task at the end. And for tasks that take the same amount of time to execute, perhaps we break ties arbitrarily. Now, if we organize our run queue the same way as before, adding new tasks to the run queue will be easy since it will just mean that we have to add a task at the tail of the queue. However, when we need to schedule a new task, we'll need to traverse the entire queue until we find the one with the shortest execution time. So a run queue really won't be a FIFO run queue anymore, since we will need to remove tasks from the queue in a very specific order based on execution time. One thing we can do is we can maintain the run queue as an ordered queue so that tasks, when they're inserted into the queue, are placed in the queue in a specific order. It will make the insertion of tasks into the queue a little bit more complex, but it will keep the selection of a new task as short as it was before. We just need to know the head of the queue. Or our run queue doesn't really have to be a queue. It can be some tree-like data structure in which the nodes in this tree are ordered based on their execution time. When inserting new nodes in the tree, new tasks in this tree, the tree may need to be rebalanced. However, for the scheduler, it will be easy since it will always have to select the leftmost node in the stream. If the tree is ordered, the leftmost node will have the smallest execution time. So we have a queue, a tree. This illustrates really that the run queue doesn't really have to be a queue. It can be other type of data structure, and we'll see that it often is based on whatever is appropriate for the scheduling algorithm.